Hello students, let us start the AEC class. Let us have a brief recap of whatever we have been discussing earlier, because in these 3 days holidays, you might have forgotten many of these new concepts. So I had shown you this diagram earlier also. I have slightly updated the diagram by adding additional text boxes. All the yellow boxes indicate input and output connection types. That means for the first diagram A, you can see it is mentioned as series shunt, means input is series connection, output is shunt connection. It's the same way with all other 3 connection types. And the green box which I have included here indicates the type of feedback, means voltage is taken from the output and then it is connected in series to the input. So you can see the title given here for this diagram is voltage sampling series mixing, means voltage is sampled at the output and it is mixed at the input in series connection. So now this is a voltage series feedback amplifier, and we can also call it as voltage to voltage conversion, because input is also voltage, output is also voltage. Coming to the diagram B, we can see it is mentioned here as current sampling and shunt mixing, means at the output current is sampled and it is connected in shunt at the input. And I had told you earlier also, whenever we have shunt connections, we will have to use current source at the input. The reason is, if at all we have 2 voltage sources in parallel, it will be very difficult to analyze that. In the sense, whenever there are 2 voltage sources which are in series, always there will be linear addition or linear subtraction depending upon the waveforms. That means if one waveform is in the positive cycle, if the other waveform is in the negative cycle, the resultant waveform will be the subtracted version. If they are in the same phase, then the resultant waveform will be in the added version. But when 2 voltage sources are in parallel, we have difficulties, because when 2 voltage sources are in parallel, whichever is having the largest potential is going to be dominant. We cannot say that a linear addition or a linear subtraction is going to happen there. That is why whenever we have the shunt connection at the input, we are replacing the input with the current source and not with the voltage source. So you can see in the yellow box it is shunt series, means input is shunt connection, output is series connection, whereas the feedback type is current shunt feedback type. So now we can say, as the input is current and as the output is also current, we can say it is a current to current amplifier. We can also call it as buffer amplifier. Now coming to the type C or the diagram C, here input is also in series and output is also in series connections, and it is mentioned as current sampling series mixing, means at the output current is sampled and to the input it is mixed in series, which means it is a current series feedback amplifier. At the output current is sampled, at the input it is connected in series. So at the input it has to be voltage connections only. So we can say it is a voltage to current conversion amplifier. You can see the A diagram. The diagram A is mentioned as basic voltage amplifier. Diagram B is mentioned as basic current amplifier, whereas diagram C is mentioned as basic transconductance amplifier. Means input is voltage and output is current. So we can say it is a voltage to current conversion amplifier. Sometimes this is required. Let us say we have a buffer, and to the buffer we need current as the input. Whereas let us say at the left side we have the normal voltage amplifier. In between we need a voltage to current amplifier. That is called basic transconductance amplifier. And lastly, coming to the fourth one, it is called voltage sampling and shunt mixing. At the output, voltage is sampled and at the input it is connected in shunt. That means it's a shunt connection. Now this is a voltage shunt feedback amplifier. Whenever we have a shunt connection, we need a current source only here that I have mentioned earlier. So now this is input is current and output is voltage. So it is a current to voltage converting amplifier. Now that is called as a basic trans resistance amplifier. In the sense, let us say we have a buffer and buffer's output is current. Now let us say at the right side we have a voltage amplifier. We require a current to voltage conversion. That is where we use the basic trans resistance amplifier. In the next semester, when you are going to study a course called linear integrated circuits, you are going to study more about a beautiful circuit called operational amplifier circuit. You already have studied it in smaller details in the first year. You are going to study that particular circuit in much larger detail. There you will learn about how op-amp can be used as a current to voltage converter, voltage to current converter. Op-amp can be used in all these four types also. As a basic voltage amplifier, as a basic current amplifier, as a basic trans conductance amplifier, and as a basic trans resistance amplifier. That means it can be used as a voltage to voltage converter, current to current converter, and voltage to current converter, and current to voltage converter. Okay. So with this brief recapitulation, let me proceed to my next slide. In fact, this slide also I have shown you already in the previous class, but there was some error in this particular tabulation. I did not completely verify my table at that time, but while I was discussing this table in the last class, I thought there is something wrong here. So later on I verified. Now I have corrected this particular table fully. So let me briefly tell about it again. The characteristics of all the four amplifier types can be improved by the proper application of one of the following four feedback connections. The four amplifier types are already being discussed. Now there can be four feedback connections: voltage series, voltage shunt, current series, current shunt. Now we have four signals there. One is the source signal, we called it as Vs, and we have an input signal, we called it as Vi. We had an output signal, we called it as Vo. We had a feedback signal, we called it as Vf. Now in case of voltage series, all these four signals are voltage only. Source is also of voltage type, input is also voltage, output is also voltage, feedback is also voltage. But in case of voltage shunt, we had replaced the input with current source. So source is current, input is also current, feedback is also current, but output is voltage. Now coming to the third one, current series. In this case, output is current, but the input, as it was a series connection, it was voltage. So source is voltage, input is voltage, feedback is voltage, but output is current. But in case of current shunt, even at the input we had a current source only, so everything is current here. So you can see voltage amplifier and trans conductance amplifier, trans resistance amplifier, current amplifier, that way. Now in this voltage shunt, where input is current, output is voltage, so it is a current to voltage converter. Whereas in current series, input is voltage and output is current, so it is a voltage to current converter. Whereas the first one and the last one are basically voltage and current amplifiers only. So there was a slight error in the previous class's discussion that I have corrected it now. Now, as you already know, we have discussed this also. Series feedback increases input impedance, whereas shunt feedback decreases input impedance. Voltage feedback decreases output impedance, whereas current feedback increases output impedance. You can easily remember this. Always the series and shunt connections are at the input side, whereas this voltage and current terminologies are used in context with the output side. So whenever you remember this voltage series feedback, voltage is taken from the output and it is connected in series to the input. So whenever voltage is taken at the output, output impedance is going to be reduced. And whenever series connection is there at the input, input impedance is going to be increased. This way you can easily remember. Always we want input impedance to be increased and output impedance to be reduced in case of a voltage amplifier. Right? So that way, output voltage is taken, it is related to output only. So remember output impedance and remember reduction of output impedance. Now series connection is at the input only and it is related to input impedance. Remember it as input impedance and remember that input impedance is going to be increased. Now you can easily remember again, whenever there is a voltage shunt, you can say output impedance is going to be reduced and input impedance is going to be reduced again because of shunt connection at the input now. Now in case of current series, output impedance is going to be increased and input impedance also is going to be increased because series connection at the input is going to increase input impedance, whereas current feedback at the output is going to increase the output impedance. Lastly, in case of current shunt, output impedance also is going to increase, whereas the input impedance is also going to increase, right? Because it is a shunt connection. So always remember, series connection at the input, input impedance is going to increase. Shunt connection at the input, input impedance is going to reduce. I think I told reverse in case of current shunt. Whenever there is shunt connection at the input, input impedance is going to reduce. Wherever there is a current connection at the output, output impedance is going to increase. So, voltage series, it is output impedance reduction, input impedance increase. Voltage shunt, it is output impedance reduction, input impedance reduce. Current series, it is output impedance increase, input impedance increase. Current shunt, it is output impedance increase, input impedance reduction. So that way, series feedback increases Zi, whereas shunt feedback decreases Zi. Voltage feedback decreases Zo, whereas current feedback increases Zo. This can be remembered by relating output and input together. Now, as a summary of formulae, we have already discussed about the derivations of these in brief. In today's class, again, we are going to deal with them in detail because I am going to share my notes with you in today's class, where in the notes I have written distinctly all the 4 types with the distinct derivations. Whereas in the textbook, it was discussed together. That is, in the textbook, it was discussed, all the 3 derivations along with the diagrams was discussed together. To be able to be of more help to the students, I have written a notes in which I have separately written all the 4 of them with all 3 derivations differently or distinctly. So I am going to share it later on. But you have already seen this particular derivation in the previous class. Let us have a remembrance once again. Closed loop impedance ZOF. In case of voltage series, it is ZO divided by 1 plus A beta. That means, in case of voltage series, output impedance is going to be reduced. In case of voltage shunt also it is going to be reduced because it is related to voltage at the output. Whereas in case of current, it is going to be increased. It is ZO into 1 plus A beta. In case of current shunt also it is ZO into 1 plus A beta. Now coming to input impedance, it is always connected to series shunt connection to the input. So the series feedback is going to increase input impedance. So it is Zi into 1 plus A beta. But shunt connection is going to reduce the input impedance. It is Zi divided by 1 plus A beta. Again, series connection is Zi into 1 plus A beta. Shunt connection is Zi divided by 1 plus A beta. So, if you recall the tip which I had told you earlier, you can easily remember all these formulae. That has been my method of remembering this formulae. Whenever I relate voltage with output, output impedance, current with output, again output impedance, voltage is going to reduce the output impedance, current is going to increase the output impedance. When it comes to the input, it is series or shunt connection. Series connection is going to increase the input impedance, whereas shunt connection is going to reduce the input impedance. That way, all these 8 formulae can be easily remembered. With this, I am right now stopping the slideshow. I'll have to move on to chalk and talk if it is a regular offline class. Now, instead of this chalk and talk, let me stop sharing the PPT. Let me start sharing the PDF, so that in the PDF, let me show you the derivations. So now, I am showing you the very first connection out of the 4 feedback connection types, that is voltage series feedback. You are already familiar with this diagram now, but let me make you more familiar by discussing a little more about how we wrote this amplifier here. You can see the amplifier's block is written as input impedance Zi, that is open loop input impedance Zi, and as we are taking output as voltage, I have written the voltage source here, which is A into Vi, and then we have output impedance is in series because we are regularly discussing the voltage amplifier. So in case of a voltage amplifier, output impedance will be in series, whereas input impedance is shown as parallel. Now what is this A? As input is also voltage, output is also voltage, A is nothing but V0 by Vi. So we can write V0. I should specifically use VO instead of V0. Using V0 has been a habit. Now I think we should change, because VO stands for output and Vi stands for input. So VO is equal to A into Vi, or A is equal to VO by Vi. So in this particular connection, A is nothing but voltage gain. Please remember, this A is a changing term in the next connections. It is not going to remain the voltage gain in the next 3 connections. It is going to change. But anyhow, let me tell about that in the next circuit. So now, when we connected the amplifier in this manner, we can have a voltage connection at the output and we can have a series connection at the input. You are familiar about other things. Now you can see that at the input, Vs is in parallel with Vi and Vf together. That means we can directly write it as Vs equals Vi plus Vf. Or we can always write Vi equals Vs minus Vf based on these connections. So using all these terminologies, let us derive the basic equations. Actually, you are already familiar with these basic equations. Still, let me recapitulate. Now, the gain is VO is A into Vi. Vi is Vs minus Vf. So, gain VO is equal to A into Vs minus A into beta into VO, because Vf is nothing but beta into VO. Or we can rearrange these terms to write it this way. 1 plus A beta into VO is equal to A into Vs. So, now the gain with feedback AF is V0 by Vs. Vs is the voltage at the input signal source. So, V0 by Vs is nothing but 1 by 1 plus A beta. You can see from the upper equation. So, this is a standard equation which is going to be derived in the same way for all other 3 feedback connections. Now, coming to the input impedance, II is equal to Vi by Zi, where Zi is the open loop input impedance, that is the impedance of the amplifier. Now, Vi is Vs minus beta into V0, right? Because Vi is nothing but Vs minus Vf. Vf is beta into V0 divided by Zi. Now, V0 or Vo is again A into Vi. So, it is Vs minus beta into A into Vi divided by Zi. We can rearrange this equation as Vs is equal to II into Zi plus A into beta into II into Zi. Now, input impedance with feedback is Vs by II. Isn't it? Vs is the signal at the input source. So, input impedance with feedback is Vs by II. So, that is Vs by II is nothing but Zi plus A beta into Zi from the equation that is shown at the upper side. So ZIF is equal to ZI into 1 plus A beta. That means input impedance gets increased by a factor of 1 plus A beta. Now moving on to the output impedance. For measuring the output impedance, now Z0 is in series at the output. ZOF is determined by applying a voltage V resulting in a current I with the Vs shorted. As you already have studied with the Thevenin's equivalence, voltage source needs to be shorted here now. So when Vs is shorted, we will have only the input as voltage V resulting in a current I, because now Z0 is in series. So now V is equal to I into ZO plus A into VI. I is the current, resultant current, ZO is the output impedance which is in series. So there is a drop of I into ZO across that output impedance. Plus we have the additional voltage which is A into VI itself. Please recall that here. I will show you the diagram again. You can see here it is I into ZO plus A into VI. That I is the resultant current when Vs is shorted. Okay. Now we have to assume this procedure because we are in the process of finding out a series resistance, that is ZO. So now V is equal to I into ZO plus A into VI. Let us substitute for VI. I into ZO minus A into VF. Why? As Vs is shorted now, Vi is nothing but minus of Vf. So Vf is nothing but beta into V. So it is I into ZO minus A beta into V, or V into 1 plus A beta is equal to I into ZO. Finally we get ZOF, or the output impedance with feedback is nothing but V by I. V by I is nothing but ZO divided by 1 plus A beta. That means the output impedance is reduced by a factor of 1 plus A beta. Okay. So you can understand, in case of voltage series feedback amplifier, input impedance gets increased by a factor of 1 plus A beta and output impedance gets reduced by a factor of 1 plus A beta. Okay, let me proceed. Okay, let us start with this voltage shunt feedback, where you can see at the input we have connected current source instead of voltage source, and we can always say that Is equals If plus II by applying KVL at the input side. And you can see here at the output it is voltage, at the input it is current. So we have written the voltage source as A into II. That means VO equals A into II, or A equals VO by II. Let me admit the student. When A equals VO by II, that VO by II is going to be called as a trans resistance. Means VO is the output voltage, II is the input current. So it is going to be trans resistance. So remember, this is like a trans resistance amplifier now. That means current is converted into voltage. You already know that we have 4 types of amplifiers, namely voltage to voltage, current to current, then current to voltage, voltage to current. There can be 4 types. Voltage itself is amplified, then it is called voltage amplifier. If current itself is amplified, it is called as current amplifier, also called as buffer. Now, if the input is current and if the output is voltage, we need such amplifiers also in some of the applications, where at the input side there can be a current and which we wanted to be converted into voltage at the output. Then we can also call it as a trans resistance amplifier. You are seeing such connection here now. Along with the feedback connection, you are seeing that way only. So this is a current to voltage converter. Similarly, on the other hand, we can have a voltage to current converter. Then that is called as a transconductance amplifier. So right now whatever you are seeing is like a trans resistance amplifier along with feedback connections. So remember this particular diagram. Let us try to derive the equations for this. As I have told you, here A equals R into M, which simply means this R is resistance, M is mutual. Just like we had that symbol called GM, where G was conductance and M was mutual, and we called it as transconductance. So we can call this RM as trans resistance. Now using this particular diagram, let us derive the three equations. So gain here is VO equals A into II. IS equals II plus IF, as already told earlier. IF is nothing but beta into VO, because that is the feedback current. So VO is nothing but A into II. So IS equals II plus beta into A into II. Therefore, the feedback gain is V0 by IS. You can see it is a trans resistance here also, because input is current, output is voltage. So the feedback gain is VO is A into II and IS is II into 1 plus A beta. That way totally II gets cancelled and we have AF equals A by 1 plus A beta. That is the regular expression which we have been getting in all the feedback connections. Now let us derive the formula for input impedance. Now input impedance ZIF equals VI by IS. Input impedance with feedback is VI by IS. Now IS is II plus IF. So input impedance with feedback is VI divided by II plus beta into VO. Now let us divide numerator as well as denominator by this term II. So it is VI by II divided by II plus beta into VO by II. VI by II is nothing but ZI, that is input impedance without feedback or open loop input impedance. And II by II is going to become 1 and beta into VO by II is nothing but A. So we have input impedance with feedback ZIF equals ZI divided by 1 plus A beta. Similarly, ZOF also can be derived as ZOF, output impedance with feedback, is equal to ZO divided by 1 plus A beta. So in this particular connection of voltage shunt feedback, you can see voltage, because of voltage, where is this? Yeah, here. Because of voltage at the output taken, output impedance is reduced. Whereas it is series feedback, voltage shunt feedback, because of the shunt connection at the input, even input impedance is reduced. Now let us go for the third connection called current series feedback. Now you can see this particular connection, current we are taking at the output and connecting back in series to the input. Now we have current at the input and current at the output. So naturally output is a current source now instead of a voltage source. And because it is a current source now, output impedance is shown in parallel to the current source. Unlike the earlier connections where we had shown it in series, because there the output was voltage. Here the output is current. So output impedance is shown in parallel along with the current source. Now this current source output is A into VI. So what is A here now? V0 is A into VI. So A is now GM. You can see at the input it is like this, VI, at the output it is current. So it is now I0, it is not V0. IO is equal to A into VI, or A is equal to IO by VI. When A is equal to IO by VI, it is current by voltage. Current by voltage is conductance. And as it is mutual or as it is transferring, it is now GM itself or transconductance. So please remember, in case of current series feedback, the gain is transconductance. In case of voltage shunt feedback, the gain was transresistance. You will have to remember these diagrams in that way only, and then only you will be able to derive the equations. So let us proceed to the derivations now. Now here the gain is I naught is equal to A into Vi. When the gain is A into Vi, Vs is equal to Vi plus Vf, or Vs is equal to Vi plus beta into IO, or again we can write the expression for IO as Vi plus beta into A into Vi. Therefore, the gain with feedback is I naught by Vs. Remember, the gain is now transconductance. Now this amplifier can be called as a transconductance amplifier. The current series feedback amplifier can be called as a transconductance amplifier because the voltage is going to be converted into current there. Earlier one was called as transresistance amplifier. It is because of the feedback connections. So now here, okay, let me continue. Here the gain with feedback is IO by Vs. It is transconductance. IO is A into Vi. Vs is Vi plus A beta into Vi. So finally Vi gets cancelled. We get A by 1 plus A beta, which is a standard expression. Coming to the input impedance, Vs is equal to Vi plus Vf, or Vi plus beta into IO. IO is again A into Vi. So we get Vs is equal to Vi plus beta A into Vi. Therefore, input impedance with feedback is equal to Vs by Ii. Substitute for Vs, Vi into 1 plus A beta divided by Ii. So Vi by Ii is nothing but Zi, input impedance without feedback. So finally we get the expression as Zi is equal into 1 plus A beta. Proceeding for the derivation of the output impedance. Now with the procedure discussed earlier, we have to make the voltage source as 0, right? At the input we have to make the voltage source as 0. Then we have I is equal to V by ZO plus A into Vi. You will have to recall that particular diagram where Vs is shorted. I is equal to V by ZO plus A into Vi is equal to V by ZO minus A into Vf, because Vi is nothing but minus of Vf because of the shorting of the voltage source at the input. So that is V by ZO minus A into beta into I, or I into 1 plus A beta equals V by Z naught. That is V equals I into Z naught into 1 plus A beta. So therefore now output impedance with feedback ZOF is equal to V by I equals, substitute for V, I into Z naught into 1 plus A beta divided by I. Now I gets cancelled, we get Z naught into 1 plus A beta. That means output impedance is going to be increased in this connection, and even the input impedance is also going to be increased in this connection. Lastly, coming to the current shunt feedback. You can see this diagram here. Here output is taken as current, and at the input also it is current because it is a shunt connection at the input. Now coming to current shunt feedback, this is current to current converter. So at the input you can see the input impedance, and output you can see the current source with output impedance connected in parallel. It is connected in parallel because of the current source. So now because of this, this is a current to current converter. We can call it as a buffer now. Now here A is equal to AI. It is current gain, because what is this A into II? It is IO. IO is equal to A into II, or A is equal to IO by II. That is the current gain. Proceeding with the derivations now. Here gain I naught is A into II. So Is is equal to II plus If at the input. If is nothing but beta into I naught. So it is 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 equal to II plus beta into A into II. Therefore, gain with feedback. Remember, this is now a current gain. It is not a voltage gain. Gain with feedback is IO by Is. IO is equal to A into II. Is is equal to I into 1 plus A beta. So II gets cancelled. It is nothing but A by 1 plus A beta. This is a standard equation. Similarly, we can derive for input impedance with feedback, that is Zi by 1 plus A beta, and output impedance with feedback ZOF is equal to ZO into 1 plus A beta. Here, in case of current to current conversion, we have input impedance getting reduced and output impedance getting increased, which is in contrast with the voltage to voltage conversion. Please recall, in case of a voltage amplifier, we had input impedance being increased because of this feedback, negative feedback, and output impedance was reduced. In contrast, in the case of a current amplifier, input impedance is being reduced and output impedance is being increased. So this way, the current amplifier can be used for impedance matching as well whenever such necessities arise in our electronic designs. Let us have a small exercise now. Determine AV, Zi and ZO for voltage series feedback amplifier having A equals minus 100, Zi equals 10 kilo ohms, ZO equals 20 kilo ohms, and beta equals minus 0.1. Why it is A is shown as minus 100? Because we already know that in general our amplifier produces 180 degree phase shift. That is why gain is given in negative terms. And beta is again minus 0.1. Why? Even the feedback network has this particular negative sign, and only 10% of the output is taken back to the input. That is why beta is minus 0.1. I have been telling you that beta is always less than unity. It is always a fraction. So we will substitute the formula simply for voltage series feedback amplifier. AF is equal to A by 1 plus A beta. You can see A is minus 100, 1 plus A beta. 100 into 0.1 is 10. So it is minus 100 divided by 11. That means the gain with feedback is only around 9.09. You can see the open loop gain is 100 times, whereas the closed loop gain is only 9 times. That is, there is a reduction in gain. But we had seen that reduction in gain is maybe one limitation, but we had other 6 advantages out of the negative feedback. Now the input impedance is Zi into 1 plus A beta, that is given as 10 kilo ohms into 1 plus 10 is 110 kilo ohms. You can see open loop input impedance was 10 kilo ohms, closed loop input impedance is 110 kilo ohms, almost 100 times increase. Similarly, output impedance is ZO divided by 1 plus A beta, that is 20 kilo ohms divided by 11, that is 1.82 kilo ohms. You can see the open loop output impedance was 20 kilo ohms, closed loop output impedance is reduced to around 2 kilo ohms. So that way, this is how we get advantages with the negative feedback. Now let us repeat the above exercise for beta equals minus 0.5. Now here beta was 0.1, 10%. Here beta can be 0.5 or 50%, which means 50% of the output is taken back as the input. So it is 0.5 now. So now substituting the same values, AF equals minus 100 divided by 51, that is minus 1.96. You can see here the gain was minus 9 when beta was 0.1. Here now the gain is minus 2 when the beta is 0.5. That means gain is further reduced. Okay, gain is further reduced. What about input impedance? Input impedance is now 510 kilo ohms. Earlier it was 110 kilo ohms. input impedance is further increased. What about output impedance? Output impedance is now 392 ohms. It was around 1.82 kilo ohms earlier. Now it is 392 ohms, means output impedance is also further reduced. So now it can be seen that ZIF gets increased further and ZOF gets reduced further when the beta ratio is increased. So this way we have the advantages of negative feedback. Now with this exercise, let me conclude today's class because it is already, the WebEx is already showing a less number of minutes remaining. So let me conclude today's class. See you in the next class. Until then, take care and goodbye.